Good evening. This is the first one I'm making in the evening. I was just so excited about talking about derivatives of trigonometric functions that I thought we would do this one in the evening. We've learned how to take derivatives of all polynomials, and we've learned the product rule and we've learned the quotient rule, but trigonometric functions are so important that we should learn how to take derivatives of them. So we have 6 trigonometric functions: the sine, the tangent, the secant, and their cofunctions. The cosine, the cotangent, and the cosecant. So how are we going to take the derivative of any function? We're going to use our basic formula, the only formula that we really have to take a derivative, and that is the limit as h approaches 0. I'm working on the derivative of the sine of x, so it would be f of x plus h. So it's the sine of x plus h minus f of x, the sine of x, all over h. Now, once we set the limit like that, then we have to do some more work until we get an answer. And I could go through all the algebra and trigonometry involved to do that. It comes into first changing the sine of x plus h into the sine of x, cosine of h plus cosine of x, sine of h. We have to use that trigonometric identity, and it just gets a little bit confusing. And so I really don't want to put you through that. Instead, I'm going to show you a slight different way of doing it. And that's actually graphing what the sine function looks like. So the sine of 0 is 0. Here's pi over 2. The sine goes to 1. And then this is at pi. The sine of pi is 0. And the sine of 3 pi over 2 is negative 1. And we can do the same thing on this side. So we have the sine function in black. Now, this isn't actually a proof, but it's a pretty good indication. When we're graphing the derivative, we're graphing the slope of the function itself. So if you look right here, you can see a slope that looks pretty much like 1. The rise over the run is about the same. So we have a point right there on our derivative. Right here at pi over 2, you can see the slope looks like it's 0. Then you get to at pi, you get a negative 1 slope. And then at 3 pi over 2, we're back to a 0 slope. And then we get back to a slope of 1 if we were to continue the sine over here. And the same thing goes on this side. We have a slope of 0 right here at negative pi over 2, and we have a slope of negative 1. And pretty much if we were to connect the dots, the function would look something like that. And what function do we know that looks like that, that starts at 1 and then goes to 0 and then to negative 1? Doesn't it look an awful lot like the cosine function? Well, as it turns out, if you actually go through all the algebra and trigonometry to solve this, it does turn out to be the cosine. So we can actually say that the derivative of the sine is the cosine. Now, the only thing I really want to make clear is when you do go through all that work, at one point in here, you get the limit as h approaches 0 of the sine of h over h. And this is something that we proved once before, that this was equal to 1. You have to use that in this proof in order to find it's the cosine of x. And if you remember back when we did this proof, I told you probably the biggest thing to take away from that proof is when we did it, we had to assume that our angle was in radians. So all these formulas that we do, it's very important to know that the angle has to be in radians for these formulas to work, to be accurate. Okay, let's see if we can do the same thing with the cosine. Really, the only way to really get the derivative of the cosine is to go through this same formula, but put cosine in place of sine. But what we're going to do instead is take a different color, let's pick green, and look at this red cosine function. So what is the slope right here? Well, it's pretty easy to see that that slope is 0. And then we go right here, at pi over 2, we see the slope of the red line is -1. And then it goes back to a slope of 0, and then to a slope of 1, and then back down to a slope of 0. On this side, we have a slope of -1, and then a slope of 0. And what are we getting? We're getting, if we connect the dots, I'm sorry, this one should have been up here at a +1. That's a +1 slope. Now we're getting a -1 slope. 0. So, if you ignore my mistake there, you can see that this green function looks just like this black function, except it's mirror imaged around the y-axis. So it's the exact same thing, but with the opposite sign. Now this again is not a proof, but it's a pretty good indication that the derivative of the cosine is minus the sine. So I'm going to put that right up here. So we have 2 of the 6 done. Now, if we're smart about it, we don't have to go back to that main definition of derivatives. Instead, we can say that the tangent is the sine over the cosine. And we already know the derivatives of the sine and the cosine. So what we can do is use the quotient rule. We have one function divided by the other function. So what we can do is say our cheer. Low, which is the cosine, d high, so the derivative of the sine, which now we know is the cosine, and then minus high, which is sine, d low, the derivative of the cosine is minus the sine. Well, minus times minus is going to be plus all over the low squared. So it's cosine squared of x. Well, it's looking kind of complicated, except what do we have? Cosine squared of x plus sine squared of x. That's Pythagorean identity. Cosine squared plus sine squared is 1. So I can cross all that out and just put a 1. And the reciprocal function of the cosine is the secant. So 1 over the cosine squared is the secant squared of x. And now we've got the derivative of the tangent. Turns out to be secant squared of x. I'm just going to do one more. How are we going to get the derivative of the secant? Well, the secant is the reciprocal of the cosine. So we can say, again, we can use the quotient rule, and the derivative is low d high. Well, the derivative of 1 is 0 because it's a constant, minus high, 1, d low, the derivative of the cosine is minus the sine all over low squared. Well, we have minus, this cancels, 0 times anything is 0, and minus times minus is plus. So we get just the sine of x over the cosine squared, which would be a correct definition. But if we know the sine divided by the cosine is the tangent, and 1 over the cosine is the secant, that makes it a little bit nicer. We don't have a quotient. It's just the secant of x times the tangent of x. So now we could do these two the exact same way, but you're probably getting tired of watching me take derivatives, so I'm just going to tell you that the cotangent is minus, and it turns out sort of like the tangent. The tangent is secant squared. This is the cosecant squared. And the same thing here. The derivative of the cosecant of x is sort of like the secant. All the cofunctions have negative derivatives, and instead of secant tangent, it's cosecant cotangent. So now we have the derivatives of all 6 of the trigonometric functions. So let me just give you one example. Say we had y equals x squared sine of x plus the cosecant of x. I think you agree, a pretty complicated looking function. But we're already set to take the derivative of that. We could say dy dx. Now, this is something where a lot of beginning students especially make a mistake. We have a function plus a function. Well, derivatives are sort of our friends, so we can say it's the derivative of the first function plus the derivative of the second function. This function and this function. But what you often forget is in this function, it's made up of the smaller function x squared times the sine of x. So we have to use the product rule. We can't just say the derivative of the first times the derivative of the second. So let's do the product rule. The first function times the derivative of the sine, which is the cosine, plus the sine of x times the derivative of x squared, which is 2x. So now we've taken care of this, and then what's the derivative of the cosecant? Well, that's just kind of a memorization thing. It's minus the cosecant cotangent. Okay. So if you know your formulas and you don't forget the product rule and the addition rule, then it really wasn't that much work for us to do, and that was a pretty complicated function. So I'm feeling pretty good about that. I hope you are. Now let's just look at one example and we'll call it a video. Say we had a spring like this that was 5 meters long, and it had a weight at the bottom of it, and it was hanging from someplace up here. And we wanted to take that spring and push it all the way up here and then let it go and try to see what its motion would look like. Well, I think if you know about springs, if you started it up here and let it go, it would come down here, and it wouldn't just stop at its natural length. It would go down here, and then it would come back. And it eventually would damp down and stop. But let's just make a small assumption that this is a little bit of a simplification, that this is a frictionless spring. So it would just keep going down and up and down and up. Well, how would we model that motion? Well, if you know the way the trigonometric functions go, especially the sine and the cosine, they go between -1 and +1. So I'm saying, what if we call the function that models the movement of this the position at time t is 5 times the cosine of t. Now, if you look at that, why did I pick 5? Because we said that this is 5 meters in length. So if we call this position 0, and this position 5, and this position -5 right down here, when t is equal to 0, I get 5 times the cosine of 0, which is 5. That would mean at time 0, the spring is right here. And then, at time pi over 2, the cosine of pi over 2 is 0, so the position is going to be 0. So the spring is going to start here, and then go to here, and then when t gets to be pi, 5 times the cosine of pi is going to be -5, and it's going to end up down here. So it's going to go from here to here to here, and then at 3 pi over 2, the cosine is going to be back down to 0, so it's going to get back to this position again, and finally, at time 2 pi, it's back up to 5 again. The cosine of 2 pi is the same as the cosine of 0. And then this process is just going to keep continue. As t goes up by pi over 2, it's just going to go through this whole cycle again, and it'll keep doing that as long as you want. So what we've done is we've modeled this motion of the spring going back and forth, and the only way you could have done that is with a cosine or a sine function. Now, let's just make the domain, let's go through this cycle twice. So it's going to take 2 pi to go through once. So let's try to make it go through twice. So we would say 0 is less than or equal to t is less than or equal to 4 pi. And it should go through twice. So let's try to model that again using that graphing utility called Desmos, and see if we can simulate and see if the motion is what we think it is. So let's try that and watch. Oops. There it goes. It goes down and then comes back up and then goes down and then goes back up. Now, one thing we haven't done is use the derivative. Well, the derivative should measure how fast it's going. So let's watch this one more time and see if we can see anything about the speed of this particle. So it seems to be speeding up, and then it's going at its fastest when it gets right here, and then it slows down, and then it speeds up until it gets here, and then it goes back up to the top. So I just want to show you what a derivative would have told us. The derivative of the position is the velocity, and what would we get? -5 sine of t. The derivative of the cosine is minus the sine. So, if we were doing the same chart and putting in the velocity, what would we know? At time 0, the velocity would be -5 times the sine of 0, or 0. And it was a 0 velocity when I let it go. And then the maximum velocity is going to happen at pi over 2. You get -5 times the sine over, it's actually the minimum velocity. It's at the maximum speed, but it's going at -5 because we're considering up to be positive and down to be negative. So it's going from 0 to -5, and then when you get to time pi, the sine of pi is back down to 0. So when it gets down into the bottom, it stops for a minute and then starts going, now it's gaining position. So at 3 pi over 2, the sine of 3 pi over 2 is a -1. So you get 5, and then you're back to 0. So it starts out at 0, it works up to a velocity of -5, then it goes down to 0, and then it goes in the positive direction, so it works up to 5, and then it goes back down to 0, and it would continue in that motion. So the velocity would have told us what it did without doing the animation, and the animation is kind of backing up our math. So now we know all about derivatives of trigonometric functions. So have a good night, and we'll see you the next time.